Welcome back. In this video, we will focus on heterogeneous conversion of reactants. In this case, the catalyst is immobilized or entrapped inside a porous particle. We will learn how the overall reaction rate is limited by the speed at which the reactants can diffuse from the bulk medium into the pores of the particles to get to the site where the catalyst is located. And there, the reaction will take place. But let us take a closer look at what happens in a continuous stir tank reactor in which reactant A is converted into a product. The tank is filled with a medium and reactant A, and in that medium you will find the porous catalyst particles, in which the catalyst is immobilized or entrapped in the pores of the particles. So let us assume that we have a gel-like particle, which is basically a highly porous particle of which the pores are filled with medium, and here we have that particle. It is surrounded by the ideally mixed medium with reactant. And around the particle itself, the medium is less free to move around, so we recognize a stagnant layer of medium. And inside the particles, you recognize the catalyst in the pores of the particle, waiting for the reactant to arrive. The reactant has thus to move from the highly mixed bulk phase through that stagnant layer to the interface of the particle. And once at the interface, the reactant has to diffuse into the pores where it can react with the catalyst. And in this case, we assume that the particles are highly porous and that the pores are filled with medium. We can therefore assume that the partition coefficient of the reactant between the gel particles and the medium is close to 1. It's also possible that the particles are rigid, with less pores in which the catalyst is immobilized. Well, in that case, the partition coefficient of the reactant between the porous particles, and the medium will be smaller than 1. It's also possible that the concentration of catalyst in the particles is relatively low. Well, in that case, the profile of the reactant in the particle will look like this. The reaction rate inside the particle, however, will be slower than the reaction rate with more catalysts present. But in general, the catalyst inside the particle will feel a lower reactant concentration in its vicinity than the concentration that you would measure in the bulk of the medium. So if you measure the reaction rate, the observed reaction rate, it will be smaller than the reaction rate that you would expect based on the reaction concentration in your medium. The observed rate is decreased compared to the theoretical reaction rate with an effectiveness factor eta E, and that will have a value between 0 and 1. The effectiveness factor is actually a result of both the decrease in concentration over the stagnant layer around the particle, caused by diffusion limitation in that layer, and the decrease in reactant concentration inside the particle itself. But most often, however, the diffusion limitation inside the particle is much larger than the diffusion limitation in that stagnant layer, because inside the particle the medium is not moving. There's only diffusion and no convective transfer, as is in the case in the bulk medium or in that stagnant layer, a part of it. On top of this, on its way to the particle center, the reactant is converted by the active catalyst site. And because of that, the external effectiveness factor can be regarded as 1, and we only need to consider the internal effectiveness factor. If this effectiveness factor were known, we will be able to calculate the required volume of our CSTR reactor. And to do that, we need to set up the steady-state mass balance of the reactant. So if we assume that the reaction follows first-order kinetics with a known reaction constant K1, and we know the concentration and feed flow, and we know how much reactant A we want to convert with the effectiveness factor, we would be able to find the required volume of the tank. I hope to see you soon to learn more on how to determine that effectiveness factor. See you soon.